Okay. Uh, Hello, my name is Harry.
I'm Marco, and this is our project. Training StyleGAN2 and applying latent space discovery techniques on a novel gemstone images dataset, or in other words, training a generative model and then having it find human interpretable features within the latent space. So the StyleGAN2 is based upon a GAN, or a generative adversarial network, which consists of two networks, one which generates and the other one which discriminates as to whether an image was generated or an image was real. And then the two sort of battle it out until they converge. And the way that the generator works is it takes in this random input, which it then transforms into an image space. And so for StyleGAN2, furthermore, is based on StyleGAN, which the way it works is instead of just putting this latent space directly into a generator, it first takes this latent space and then puts fully connected layers to learn this mapping network, which is called a style mapping. And then this style mapping is then inputted across the layers of the generator so that it, along with some noise, so that it can learn the generation of the styles throughout. And so the third thing we did was we use this system called closed form factorization. And so essentially what it is, it's an unsupervised and untrained system of interpreting the latent space or the random noise inputted into the GAN in a way that's human interpretable, such as the pose or the rotation or expression. So different features that the model learned to encode for, it can then transform into a way that humans can actually interpret them ourselves.
So for our dataset creation, we created our own dataset of diamond and other gemstone images by web scraping these images from a website called Brilliant Earth. For the diamonds, which you can see on the right side, we scraped a total of a little over 20,000 images, all with varying features. So the primary feature that we focused on in our project is shape. So on the right, you can see brown diamonds, ovals, cushions, emerald shapes, heart shapes. And there's also other features associated with these diamonds that we didn't focus on that much in this project. We also created a second data set of gemstone images, so non-diamond images with color. So one of the systems that Brilliant Earth has is they can take 360-degree images of a particular gemstone. So you can see on the bottom right that they have taken images of this one gemstone from many different angles. And we created a data set of a little over 37,000 total images of these multicolored, multi-angled gemstones. For our data preparation for the training, so StyleGAN only accepts square images with dimensions of a power of 2. So we had to add gray padding to any non-square images and also downsample all of them to 256 by 256 pixels. For our training experiments, we ran all of our experiments on Kaggle using the free GPU access. So this is showing the training progression of StyleGAN2 from scratch. So you can see that at 0 training iterations, it generates just mostly noise. And over time, it learns like the important features of a diamond and what a diamond really looks like. We can see here that because it trained from scratch, it took many thousand iterations to learn this, maybe like 3,000 to 5,000. And for this runtime, we stopped at 9,000 iterations because of the time limit on Kaggle. And what we would do is just resume training for 9,000 iterations at a time. So these are images for the second round of training from 9,000 to 18,000 training iterations. You can see that the generator is definitely improving over time. And this is the last batch of training we did on the diamonds data set from 18,000 to 27,000 training iterations. And by the 27,000th training iteration, the generated diamonds look really good and realistic. And we think that the generator has done a really great job. So this is just some final sample images generated by the generator after 27,000 iterations. You can see that some of the diamonds still look really weird, like this heart with some with a hole in the middle. But overall, the generator really understands what a diamond looks like, and some of the samples look really realistic.
So our second experiment was using the Gemstone dataset. And the way we went about this was because gemstones and diamonds are very similar in shape and size, we actually used transfer learning to train the model on these gemstones so that it could avoid having to learn all the things that it originally had to learn, such as the basic shape and the basic edges and all the basic features of a diamond. And so because of this, after about only 2K iterations, it was able to learn the features of a gemstone, and then it could quickly further improve from there. And so it was able to learn features such as rotation, color, and shape. And so we trained it for a total of 36,000 iterations, and the images look really good and definitely demonstrate all three of these properties that we were really looking for. So we then went on to apply closed form factorization, which, if we recall, it takes this input space, this random noise input space that the generator takes in and converts it into a human interpretable form. And so each of these samples, what's occurring is along a specific vector or specific direction within that latent human interpretable latent space, it's moving a certain number of degrees or a certain step length from a negative to a positive. And we can then interpret what these directions actually mean. And so for the first one, it seems to be that as we move from one direction to the other, the sort of center of mass of the diamond comes from the top and moves down towards the bottom. So we'll start seeing hearts at the beginning, and eventually they'll move downwards to circles and ovals, and eventually down into pear shape. And the third, for example, the third direction seems to start with narrower diamonds or smaller diamonds, and eventually they expand to fill the screen. And so it seems to be encoding for size in some aspect. And after about the sixth or so, most important vector, or biggest impactful vector, it seems to encode very little within the rest of the vectors. And so it mostly seems to encode for shape. So we applied the same analysis to the gemstones, which was a little more difficult because there were three types of features that we were really looking for: shape, rotation, and color, as opposed to just the shape of the diamonds. There's definitely a lot more entangled, but also a lot more vectors which all show these sorts of rotations. And so very clearly within each of these, there is some sort of rotation which is uniform between each of the samples. There's a color change which is for the most part uniform, such as if the colors all start out dark, they'll eventually come out to a lighter color, such as the second row, where we can see they're mostly starting off as a dark green or medium to dark green, and they're squares, and they eventually rotate around and turn lighter, and eventually all become pink and small. And so it's kind of hard to interpret exactly what some of these features are, but we can see that there's very clearly a systematic change in color, rotation, and shape throughout each specific vector or each human interpretable direction.
So in conclusion, we reached all of our project goals and gained some really valuable experience with the entire machine learning pipeline. So we created our own data set of diamond and gemstone images. Then we trained StyleGAN2 to learn how to generate the images that look like the ones coming from our data set. And we also used the closed form factorization technique to identify eigenvectors in the latent space that can control for some important output features in the generated images. So our diamond model learned important components that make up what looks like a diamond. And the gemstone model also learned a diverse set of shapes, colors, and rotation features, as well as how to transition these features in the latent space. In our opinion, with our limited GPU access on Kaggle, we think that we did a great job teaching the generator how to generate these awesome, realistic looking gemstones.
Some future work we'd like to do. To begin with, we were hoping for a little more pure encoding within each of the directions. So we'd like to find a solution that can better distinguish between these between rotation, shape, and color, because currently they're somewhat intertwined. And if we were able to get that to work, where each one is a specific, one direction is a color change, one direction is a rotation change, one direction is a shape change, then we could actually use that in the generation process and be able to say, we want a gemstone of this color, of this rotation, and this shape, and we'd be able to make one of using these eigenvectors. We'd also like to utilize the associated features that have been labeled with each of these diamonds from Brilliant Earth, such as clarity, cut, price, and shape. And by teaching the generator to learn these features and output them, and then teaching the discriminator to discriminate based on them, we could hopefully teach it to learn these features, and then using the same closed form factorization that we used before, we could then have it hopefully learn these as interpretable directions, which we could then use to go through the direction space. And then the other two improvements for the future would be with our data sets. So the first one is that we didn't use angles. We didn't use the different angles for the diamonds, but it would be very interesting to see how the diamonds respond to the whole pipeline of using training on angles and then using closed form factorization, as well as making a data set with a better distribution of features, because within our data set, oftentimes certain colors there might be more of one color, or especially with shape, there's definitely an uneven distribution of shape. And so by fixing that, we might have better results.
Okay, so thank you for watching our presentation. If you'd like to read the full report or reproduce our work, you can go to the GitHub and visit our repository. Or if you would like to see the output, our data set and the output models and images and videos, you can go to the box link.
Thank you.
Cool.